Oh, she is?
Yeah, my brother.
Ah. She said she wasn't feeling well.
What do you guys
But
do?
you don't need to feel well to play a game of leagues.
It's so true. But if you're coming here to sit down and learn math, then you just don't feel well.
She's just thinking about you guys. She wants you to feel well as well.
Sure appreciate that.
I know, quite kind of her, right?
So nice.
Alright, so let's start by doing a recap of all the definitions that were used in the book so far. Now, just keep in mind, what we did is we covered logic from one textbook. Then we covered the axioms of arithmetic, those 10 basic field axioms, which had nothing to do with any textbook. I just gave those to you. And we did some proofs based off of it. And then we jumped into this book. And so this book, and what you've already proved, there's going to be a little bit of discrepancy there. Because what we did was way more rigorous. Now we're going to get into this book. It's going to feel like the author's kind of just throwing stuff at you left and right. And you're like, well, how do we know that? And he's not going to take the time to prove it like we already did. So to note something, just jumping ahead, the author just kind of throws at you the fact that if a times b equals 0, then a equals 0 or b equals 0. And that's something we formally proved before.
Yeah.
There's one example of one of those discrepancies that you'll see. Don't let me go past that squiggly line without moving the camera. That's what squiggly line means. Okay, so recap on now just material from the book, nothing else. Starting out with its basic definitions that it started with. So from the book, our first definition was that of a rational number. So a real number x is said to be rational provided that, now get comfortable reading this dense notation because I'm not going to stop writing it. There exists p, q in the integers with q not equal to 0 such that x is equal to p over q. So now I'm just going to read it how we would normally read it. Provided that there exist two integers, p and q, with q not equal to 0, such that x is equal to p over q. In other words, a number is rational if I can write it, if I can express it as an integer over an integer. Like 5 over 2. Coming back to you?
Yeah.
Alright, let's go back to some of our sanity checks. Is 17 a rational number?
Yes.
Mm-hmm.
How do you know?
17 over 1.
Because we can write that same number as 17 over 1. What's another tricky one? What about 0? Is 0 rational?
Yes.
How do you know?
0 over 1.
97, but you were close. Yeah, so 0 is rational. Notice that there isn't the one unique way to write the number. It's just if you can express it as any two integers over each other, then it's rational. Let's try another one. Is that a rational number?
No.
You guys know what pi is?
Yeah.
Okay,
It looked like something
Sorry.
over 11.
that's a pi. Is pi rational?
No.
No. What about square root of 2?
No.
No.
No. What about the square root of 2 over the square root of 3?
Yeah.
No.
Why?
Huh?
Why?
That's an irrational, and they don't cancel out in any nice way.
True, but
I mean, I'm not going to prove it.
isn't it the same thing?
just
as
giving you
7
intuition.
over 1? Only 7 and 1 are rational.
That's irrational. That's not an integer. That's not. What are the magic two integers you have in mind? How can I rewrite this number as two integers? It's not the same thing as 2 over 3. It's drastically different.
Right. But, okay.
So, let's see some more. What about 5 square roots of 2 over 7 pi? Is this number rational?
No.
No. Let's try another one. What about 3 pi over 7? Is that rational?
No.
No. Let's try another one. 13 pi over 9 pi. Is that rational?
Yes.
It is?
Yes.
What's the magic numbers then? What's my numerator, what's my denominator?
13 over 9.
No, 26 over 18, right?
Oh, my bad.
Or 13 over 9. But if you can express it as a quotient, the same exact that number, remember, that's just a symbol for some number. We have a lot of different symbols for writing the exact same number. That's one symbol for a number, and this is another symbol for the same number. This is another symbol for the same number. Good? Okay, back. Hopefully got some good intuition for rational versus irrational. And for what that definition's saying. Okay, now just a note, because I write these symbols so much, you just need to get comfortable with them. This n with an extra line going this way is shorthand for the set of all naturals. For this author, he defines the naturals to be the numbers 1, 2, 3, 4, 5, 6, 7, etc. This z with another line this way is shorthand for the set of all integers. So -3, -2, -1, 0, 1, 2, 3, etc. And then this q now, this q with a line on the right-hand side, is shorthand for the set of all rational numbers. Good? And then finally, this r with an extra line on the left-hand side is shorthand for the set of all reals. Now notice that every natural is also an integer. Everything in here is also in here. That's what we mean by this symbol. This is a subset symbol. The naturals are a subset of the integers. It means everything that's a natural is also an integer. And also notice that everything that's an integer is also a rational. Pick any integer you want, -17. That's the same thing as -17 over 1. So every integer is also a rational. You with me?
Mm-hmm.
And then finally, every rational is also a real. A rational was a special type of real number. It was a real number with some property. So every natural is an integer, every integer is a rational, and every rational is a real. Another way to say that exact same thing is the naturals are a subset of the integers, are a subset of the rationals, are a subset of the reals. Good?
And you
Alright.
can skip some of those. You could say naturals are subsets of reals.
Yes. Yes, if everything that's in here is in here, and everything that's in here is in here, then everything that's in here is in here.
Okay.
Right? Another way that we often draw subsets is with Venn diagrams, or things like Venn diagrams. So if this looks kind of like this circle right here represents all the naturals, this is all the integers, this is all the rationals, this is all the reals.
Mm-hmm.
Make sense?
Yeah.
Okay, so our second definition. A real number x is said to be irrational, provided that it is not rational. Irrational, not rational, same thing. And we don't have any special symbol for the set of all irrational numbers. Okay, next definition. Given x in R, or given a real number x, says the same thing, given x in R, or given some real number x, then y in R, some other real number y, is said to be the additive inverse of x, provided that x plus y equals 0. So y is the additive inverse of x, provided that their sum is equal to 0. 0 being the, what do we call 0?
Additive identity.
Additive identity. That's why it's called an additive inverse. It gets you back to identity. So y is the additive inverse of x, provided that their sum is equal to 0. And since there's one and only one additive inverse for every number, we represent the additive inverse of x as negative x. So negative x is shorthand for the special y that satisfies this equation. If you say negative x, you know what we're talking about, the number such that when you add it with x, you get 0. That's what negative x means. So if I tell you that x is equal to negative 17, what's negative x equal to?
17.
Just 17. Then negative x is equal to negative 17, which is the same thing as just 17. Negative x always just stands for the number you need to add to x to get 0. The number I need to add to negative 17 to get 0 is just 17. right?
Yeah.
Okay. So next, our definition for division. This book's definition for division, remember last time we used division is the same thing as multiplication by the multiplicative inverse. This book's not going to use that definition, but they're logically equivalent. So definition for division. To divide b, some real number b, by some real number c, where c is not equal to 0, means to find a number x such that b is equal to c times x. So if I know that x is equal to b over c, b divided by c, that's the same thing as finding an x such that x times c equals b.
Okay.
With me so far?
Yeah.
We call b the dividend, so whatever is right there we call the dividend. We call c the divisor, and we call x the quotient. Quotient, dividend, divisor. Good with that terminology?
Yeah.
And we have a few different ways that we can write it. We can write it as b over c, b divided by c, or the ratio of b to c. This one's one that you typically see in like a chemistry class, for example.
Yeah.
Means the same thing. So a bunch of different ways that we write division. Typically, I'll just use this way of writing it. Most standard. So that's our definition for division. So maybe write it out really quick. Let's write one. So what if I want to do something like 10 divided by 2? What does that mean? That means I need to find the magic x such that 10 is equal to 2 times that x.
Yeah.
So if I want to know what is 10 divided by 2, by our definition, that means to find the x such that 10 is equal to 2 times that x. That's using our definition right here. When we say x is equal to b divided by c, we mean b is equal to c times x. Is there anything confusing about that? And so obviously the answer is 5. 5 is the magic x such that 2 times that gives you 10. Nothing weird there?
Or negative 5.
Negative 5 divided by what?
What do you mean divide?
Should we do negative 25 divided by 5 and see what that is?
Sure.
So if I have x is equal to negative 25 divided by 5, that means I am looking for the magic x such that negative 25 is equal to 5x. What's the magic x that satisfies this equation? Negative 5. So negative 25 divided by 5 is equal to negative 5. Let's try this one. What about if I did negative 25 divided by negative 5? Now what's my x?
Negative 5.
Just 5, right? And so you'll notice that a negative divided by a negative gives you a positive.
Is that like a term or something?
Unknown fact. A negative divided by a negative is a positive. A negative times a negative is a positive.
Like when you're finding theorems for division, do you want to use it based on the b divided by c, or do you want to do it on the a equals b times c?
It's the same thing. To say that x is equal to b divided by c is to say that b is equal to x times c. They'll say the exact same thing.
So does that mean you can use like multiplicative theorems and apply it to division?
Yeah. You go from here to here, and then you can multiply both sides. And then you can go back if you want.
Okay.
So you can go back and forth between it like this. Right? So to do something really simple, notice that b over c is the same thing as, well, no, we'll get to that proof down there. We'll do some proofs with it. Anyway, so there's our definition for division. Now let's go over our definition for subtraction. Now remember last time we defined subtraction as adding the additive inverse. That's not how this book's going to define it. It's going to give something logically equivalent, just different.
Okay.
That's what I meant by we'll have some discrepancies. So to subtract c from b means to find the x such that b is equal to x plus c.
Yeah.
So if I know that x is equal to 10 minus 4, that means, if we rewrite over here, that means 10 is equal to x plus 4. And what's the x that makes this true? 6. So 10 minus 4 is 6.
Okay.
Make sense? Nothing weird there? Now, obviously I don't like the author's definitions. I like the way that we thought about it. So we'll do one quick proof now. Our quick proof is going to be, we're going to show that for any two real numbers, b and c, remember what that symbol is. That's the universal quantifier for all. For all b, c in the real numbers. For all real numbers, b and c, or for any real numbers b and c, for any two real numbers b and c, then b is equal to x plus c if and only if x is equal to b plus the additive inverse of c. In other words, notice what this is. This is the definition for b minus c, right? Or c minus b. To subtract c from b is the same thing as b is equal to x plus c, right? So this is the same thing as subtracting c from b, or b minus c. So here's b minus c, and I'm showing that it gives the exact same thing as just taking b and adding the additive inverse of c, because that's how I'd rather think about it. I'd rather think about b minus c is the same thing as b plus the additive inverse of c, and that's what we're going to prove. Because b minus c by definition is this, and I'm going to show that that gives the exact same thing as this. You with me? And then I'll think about it this way from here on out, rather than the definition the author gives. But that's what we're going to prove. So, let x be any real number such that x is equal to b minus c. Or b is equal to x plus c.
Yep.
Same thing. X equal to b minus c by definition is the same thing as b is equal to x plus c. That's what our definition says. If x is equal to their difference, that's the same thing as b is equal to x plus c. You with me? So I'm going to start out with, let x equal b minus c, or in other words, b is equal to x plus c. And I'm going to show that if this is true, then this is true. And then I'm going to show that if this is true, then this is true. Therefore, they say the same thing. Logically equivalent. So let x be a real number such that b is equal to x plus c. Well, then I can add the additive inverse of c to both sides. So then b plus the additive inverse of c is equal to x plus c plus the additive inverse of c. Now what is c plus its additive inverse?
0.
0. Right? And then what's x plus 0?
X.
X. So b plus minus c is equal to x, which is what we wanted to show. We just really showed that if b is equal to x plus c, then x is equal to b plus the additive inverse of c. B plus the additive inverse of c is equal to x. Same thing. See that? Now we'll go the other way. So now we let x be any real number such that x is equal to b plus the additive inverse of c. And I'm going to show that if this is true, then, now we're going the other way. We're going to show that if this is true, then this is true. So I'll start out with this being true, show that implies this is true. So x is equal to b plus the additive inverse of c. What am I going to do? I'm going to add c to both sides. So then x plus c is equal to b plus the additive inverse of c plus c. Once again, the additive inverse of c plus c is 0, and b plus 0 is just b. So x plus c equals b. So we showed that this implies this, and we showed that this implies this. Therefore, they're logically equivalent. So therefore, b equals x plus c if and only if x is equal to b plus the additive inverse of c. Follow that?
Yeah.
Okay. Next, our definition for our absolute value function. So when you put two vertical lines around a number like this, that means you're taking that number's absolute value. You with me so far? And so the absolute value of x, here's this definition. Absolute value of x, what does it give you? The absolute value of x is just equal to x if x is a positive number or x is 0. So if x is a positive number or 0, then the absolute value of x is just x. If x is a negative number, then the absolute value of x is negative x. So the absolute value of x is negative x. If x is a negative number, the absolute value of x is just x. If x is a positive number or x is 0. With me so far?
Yeah.
Let's try it. What's the absolute value of 2?
2.
2. How did we get that? So we plugged in 2 for x, right?
Yeah.
Now, is 2 negative? No. Is 2 positive or 0?
Yes.
Yes. So when I plug 2 in for x, then it just spits out x. Or in other words, it just spits out 2 in this case. Now I know that it's simple for you guys to just spit out what the absolute value of a number is, but I want you to make it connect with this definition. And see how the definition gives us the answer, rather than just spitting out what you've memorized the answer to be. I want you to get comfortable with the definition. So let's go over to the next one. What's the absolute value of negative 19? When I plug in negative 19 into this function, is negative 19 a positive number?
No.
Is it 0?
No.
Okay, is negative 19 a negative number?
Yeah.
So we spit out negative, whatever the symbol is here. The symbol we plugged in was negative 19, so we spit out negative 19.
So 19.
So 19, but negative 19. That happens to be the same thing as 19, but I want you to see it as negative 19.
Right. Okay.
Let me rewrite that with some space. So the absolute value of negative 19 is equal to, so we replaced our x with a negative 19, that's what we plugged in for x, so it spits out negative 19, which happens to be the same thing as just 19. Negative 19 and 19 are the same thing.
Yeah.
Good?
Yeah.
All right. So now, what's the absolute value of negative 3?
3. Negative 3.
Negative 3. Just negative 3. Is negative 3 a negative number?
No.
Is it 0?
No.
So it's a positive number, right?
Yeah.
Yeah.
So negative 3 is a positive number. So if x is a positive number, you just spit out x.
Right.
Oh.
So just spit out the same symbol.
Yeah.
And that same symbol happens to also be 3, but I want you to be comfortable with how the definition actually works rather than just saying the number. You get comfortable with that definition? Okay, so now let's imagine that a is equal to 7, b is equal to negative 3, and c is equal to 0. With me so far? Okay, so then the absolute value of a is, tell me it in terms of its letter. Is it just a or negative a?
Negative.
A.
It's a.
Oh, yeah.
b is equal to negative 3. What's the absolute value of b in terms of b? Is it b or negative b?
B. B.
B, right?
No.
No, negative b. Is b a negative number?
Yeah.
Yes, b is negative 3. So is b a negative number?
Yeah.
Yeah. So the absolute value of b, when it's negative, is negative b. It's such a simple definition, and yet kids get so confused about this definition because they never stop to actually think about what the definition is giving them. They just say, oh, if it's a negative number, make it positive. And if it's positive, leave it alone. And that's all they think about. They never think about actually plugging things into that definition. And it causes a ton of headache for you by the time you get to a real math class like calculus. And I have to re-explain what absolute value is 10 times. Because you never get it. So, b is a negative number. And so the absolute value of b is negative b. And kids hate that. You take the absolute value of a symbol and there's a minus sign there. Oh my goodness. That's broken. I got a negative number out there. No, that's not a negative number. That's the additive inverse of a negative number, which happens to be positive. All right. So the absolute value of c now is
C.
just c. Good. Feel like you're getting comfortable with that one?
Yeah.
It's a tough one. It's tough because it's deceptively simple, not because it's super complex. It's just because you always think you understand it before you really understand it. Okay, so moving on now. Let b be a positive number, and c be a negative number, and b be equal to the absolute value of c. All right, a lot of information there.
Yeah.
Absorb it, and then we'll continue. So b is some positive number. Who knows? Could be something like 3. c is a negative number. Could be something like negative 3. And b is equal to the absolute value of c. So if b is 3, c has to be negative 3. If b is 10, c has to be negative 10. If b is the square root of 2, c has to be negative root 2.
Okay.
So b is positive, c is negative, and yet b is equal to the absolute value of c.
Okay.
You with me?
Mhm.
So then I want you to compute for me, what is b plus c?
0.
0. Now let's actually prove that though, rather than just spitting it out from intuition because I gave you numbers. Let's actually think about it. b plus c, what do I know?
That B is positive.
What do I know about b?
That is positive. And
I know it's positive. What else do I know?
that it's equal to the absolute value of C.
It's equal to the absolute value of c. So I can rewrite this as the absolute value of c plus c, right? Now what is the absolute value of c?
Negative C.
Negative c! Wonderful! C is a negative number. The absolute value of a negative number is negative of that number. So this is equal to the additive inverse of c plus c.
Which is 0.
And the additive inverse of c plus c is equal to 0. So you had a hunch that the answer was 0 based off of plugging in some examples. But here's how you show you know that it's 0. And anyone can plug in examples and say, oh, so I'm going to guess it's 0. It's a whole other world when you ask a kid to prove that it's 0. Now they're lost. And here's how you prove that it's 0. You have to use your given information.
Yeah, but couldn't we have just said if B is positive and C is negative, then a positive and a negative added together is 0.
A positive and a negative added together is not 0.
Oh.
So no, that doesn't work.
Okay.
Okay, so now let's do some examples of multiplication. The thing the author wanted you to note here, make the note out loud. If I'm multiplying a bunch of terms together, let's ignore his for a second. Forget those. If I'm multiplying negative 1 times negative 3 times negative 7 times negative 2 times negative 1, when I multiply all these together and I get my answer out, will it be a positive number or a negative number?
Negative.
Negative?
Yeah,
It's an odd number.
because there's 5 negatives.
Wonderful. If you're multiplying an odd number of negative terms together, it comes out negative.
Yeah.
If you're multiplying an even number of negative terms together, it comes out positive. And so when you're multiplying terms, what everyone does in their heads is first they ignore all the signs and they just multiply the numbers. So they just do 1 times 3 is 3, 3 times 7 is 21, 21 times 2 is 42, 42 times 1 is 42. So we put our 42 here, and now the only question is it positive or negative? So then we go back and count how many negative numbers we had. 1, 2, 3, 4, 5. Ah, that's an odd number, so it comes out negative 42. And that's what people are doing in their heads when they do multiplications of a bunch of numbers like this. You with me?
Yeah.
So let's try another one. We'll do negative 1 times 1 times 13 times negative 2 times 1. All right.
26.
26. So multiplying all the numbers together, 1 times 13. So 1 times 1 is 1, times 13 is 13, times 2 is 26, times 1 is still 26. And now we count our negative signs. We have 1, 2 negative signs. That's even, so it comes out positive. So positive 26. Good? Okay. And to make sure that you know how to add together negative numbers, let's look at that one real quick. Negative 4 plus negative 12
Negative 16.
is negative 16. So when our numbers have the same signs, we just add the two numbers together, then put the sign there. What about when the numbers have different signs? So when I do negative 12 plus 4, what's that?
Negative 8.
You subtract.
Negative 8. How do we do it in our heads? First, we just look at whichever number is bigger. In this case, it's 12.
Then we subtract the other.
And we subtract the other number. So we write this as 12 minus 4. Is how we think about it, which is 8. And then we say whichever one was, if the negative number was bigger, we put a negative sign there. If the positive number was bigger, we put a positive sign there. In this case, our negative number was bigger. So it's negative 12 minus 4, which is the same thing as negative 8. Because 12 minus 4 is 8.
Are these theorems or are they
No.
just tricks?
These are tricks. These are what people are commonly thinking in their head when they're doing problems like this.
Okay.
So ways to help you think about it so that you don't confuse yourself dealing with negative numbers.
Okay.
Good?
Yeah.
Okay. And then note, we already proved this previously. The author just notes it, so we'll note it once again. A times B is equal to 0 if and only if A is equal to 0 or B is equal to 0. Another way to say the exact same thing is, I can't have two numbers when I multiply them together equal to 0 unless at least one of the numbers was 0. I can't take two numbers that aren't 0, multiply them together, and get 0.
Yeah.
Yeah.
So if when I multiply two numbers together I got 0, one of those two numbers had to be 0. Make sense? Okay, next, parentheses. There's three different ways that we write parentheses, just based off of what's useful. So we choose from context. We call those often open parentheses, we often call these closed parentheses, and we often call those brackets, but they all act the exact same way. We just use different symbols to help you figure out what pairs with what. Make sense? And you're probably already used to seeing those symbols all over the place. In fact, we've been using them all over the place so far. But we'll make special note of them. Okay, next. Adding a minus sign in front of parentheses changes the signs of all the terms inside the parentheses. Adding a minus sign outside the parentheses changes the sign of all the terms inside the parentheses. So let's see what that means from some examples.
Doesn't it just give you the additive inverse of each thing?
Yeah, you can think about it that way too. So, let's really quick note. Negative 12 plus 4 plus 3 is what?
Negative 5.
Yeah.
Yeah? Everyone see that? Negative 5? Okay, so that's negative 5. So now, if I were to add a negative number in front of there, then I should get
5.
positive 5, right?
Yeah.
Yeah.
Oh, yeah. I was looking at your other one, sorry.
Oh, but I'm going to come at this from a different approach, so never mind. So that's equal to negative 5. Never mind. I'm coming at this a little bit different than I thought. So now, if I add a negative sign, so notice, I'm going to take the same expression right here, and I'm going to rewrite it with a negative out there.
Yeah.
If I put a negative out here, and I don't want to change the expression, then I need to flip the signs of everything inside the parentheses. So if I put a negative out here and I don't want to change it, I need to switch the signs of everything inside of here if I want to keep it the same number. So if I put the negative here, since 12 was negative, I need to rewrite it as positive. Since 4 was positive, I need to rewrite it as negative. Since 3 was positive, I need to rewrite it as negative. And notice that we still have the same number. 12 minus 4 is 8. Minus 3 is 5. So we have minus 5, which is the same thing as minus 5. So we didn't change our number.
Okay.
We often call this process factoring out a negative. So if you see this and I say now factor out a negative, what I mean is rewrite it like this. Put the negative outside and change the sign of everything inside. Very common operation. Good?
Yeah.
Okay, so let's try it on one of these terms. Let's try it on this. I'm not sure how I want to say that because I don't want to just write what that equals. So if I have this number, and here's how I'll say it. No, because I'm lying with equations. We'll just say it. Okay, so I have this number now, and I want to factor out a negative. So I want to rewrite that same number factoring out a negative. What would I write here?
Negative, open parentheses.
Negative, open parenthesis.
2 plus minus 5x plus y.
Good. Good?
Yeah.
Okay, now let's rewrite this one, but I want to factor out a negative.
Okay, you could.
Tell me what to write.
Minus, open bracket.
Minus, we'll just keep the square bracket there, just see where it lines up.
Yeah.
That doesn't matter. Okay.
Minus 3y. Plus
Minus 3.
2x minus 5 in parentheses. Close.
Who agrees with that?
No, because you wrote it wrong.
Yeah, minus 3y.
It's minus 3.
Yeah, I said minus.
Yeah, it's minus 3y.
I'm pretty sure I did that.
So you want it to be minus 3y like that?
Yeah.
Yeah.
Now you like it? You sure that we're not going to change that?
Yeah.
Yeah, because that's just x is a different independent thing.
You positive? You ready to bet your life on it?
No.
Never to bet my life on this.
No? Okay, then let's write them both out and make sure it's super, super clear.
Okay.
So let's simplify. If I rewrite this one, this is the same as 3y. Distributing that in makes that a minus 2x. Distributing that in makes that a plus 5, right? Everyone know how I went from this to this, or do we need explanation?
It's good.
We can treat that minus sign as a negative 1, multiplying it in.
Alright.
So negative times that is right there. Negative times that is right there. Good?
Yep.
Yep.
Okay, let's do the same thing here. Notice that with the plus sign here, first we'll look at it this way. Keep the negative 3y plus 2x. Well, notice that we don't need these parentheses right here. These parentheses aren't doing anything, so I can just rewrite this as 2x minus 5, right?
Yeah.
And now when I distribute through this negative, make sure you don't think that these two are in any way related. Now when I distribute through that negative, I get 3y minus 2x plus 5.
Okay. Yep, I'm willing to bet my life on it.
Okay, you're willing to bet your life on that. Good.
Yeah.
So don't forget, once we have some numbers inside of parentheses again, this is all just one number.
Yeah.
Okay.
So what you did in your thinking, this was all just some number. So you had negative that number, you switched it to positive that number, that was good.
Yeah.
I thought you guys were going to say switch that to a plus, and you didn't. So you did it right. But you didn't feel very confident about the fact that you did it right. Okay. So another way we can say it is, it's not, never mind. I'm going to say not recursive, but I realize that's probably computer science terminology.
Yeah.
Does it make sense if I say that? I don't know. It doesn't keep going into deeper levels of parentheses. You only do it on the outermost level that you're applying it to. So in other words, if I had something like, we'll use curly braces and do one more, we'll just make one up. 2x plus 5y minus 7z plus 1. And I want to put the negative there. Then this just, all that changes is I'd make this one negative and leave everything else inside alone.
Yeah.
Right.
That's what I mean by it's not recursive. It doesn't also apply inside those parentheses and inside those parentheses.
Because it'll do automatically.
That make sense?
Yeah.
Yeah.
Wonderful. Okay. Note. To collect similar terms, add their numeral coefficients. Okay, maybe coefficient. Who knows what a coefficient is? Okay, so we got a good amount that don't. Maybe I should always ask who doesn't to see if there's people. Okay, a coefficient is the number, the numeral, the number that comes before the variable. So the coefficient of this term is 2. The coefficient of this term is -3. The coefficient of this term is -5. It's just what comes in front of it. And it doesn't matter if there's only one x there or if it had a bunch. So for example, if I write 17 a, b, c, x, my coefficient is just 17.
Yeah.
What if you had multiple numbers in front of x? Or, multiple different x's.
So you're saying if I had like 17x plus 13x,
Yeah.
then the coefficient of this term is 17, the coefficient of this term is 13. These are two separate terms.
Wow.
So we talk about the coefficient of a term.
Okay.
Okay, so now to collect similar terms, we add their numeral coefficients and multiply by their common factor. So a lot of terminology in there. Let's see it in action, and then the terminology will make sense. So here I have a -9ab plus ab. What's the coefficient of this ab term?
-9.
What's the coefficient of this one?
1.
1. When there's not a coefficient written there, it's implied that it's 1. Because multiplying that by 1 doesn't change anything. I can write that exact same number this way. And so this and this are just different ways of rewriting the exact same number. So there's an implied coefficient of 1, but it's not written there. So -9 and 1. So to collect similar terms, these are similar terms, since they're only variable terms, or a and b. So to collect similar terms, add their numeral coefficients. The numeral coefficient of this is 1. The numeral coefficient of this is -9. So add their numeral coefficients together. 1 plus -9. I'll write it as 1 minus 9. You okay with that?
Yeah.
Add their numeral coefficients together, and multiply by their common factor. Their common factor is a times b.
Yeah.
A times b is a factor of this term. A times b is a factor of this term. So then multiply by their common factor, ab. And that's how you collect like terms. Or in other words, this is equal to -8 ab.
Okay. Yeah, that made a lot more sense after doing the problem.
Yeah, the example makes sense there, and the example is pretty straightforward. You could have already done that example. You need to get comfortable with terminology. You need to get comfortable with what I mean when I talk about the coefficient of a number, and what I mean when I talk about common factors of numbers. Good?
Yeah.
Feel free always to ask any questions that you want, or to ask for more examples if you want. Let's do another example of this one, just to make sure it makes sense. So now I've got 3a minus 5y minus 8 minus 3y minus 2a minus 6. You with me? Okay. So, first off, notice that there's an implied plus sign outside of here, right?
Yeah.
And when we have the plus sign outside of there, it doesn't change the sign of the terms inside. So we can rewrite this one as just 3a minus 5y minus 8. And the minus sign there, if we want to get rid of that and make that a plus sign, then we have to switch the sign of everything in here.
Yep.
So that's going to be plus minus 3y plus 2a plus 6. Right?
Right.
Yeah.
For this one, we just kept all the terms the same. Since there's a minus sign there, we changed the sign of everything inside of here. So rather than a 3y, we wrote negative 3y. Rather than 2a, we wrote positive 2a. Rather than negative 6, we wrote positive 6.
Yeah.
Good? All right. Now we're going to add like terms. So this is equal to, for our a's, all the terms that have an a in it, we have 3 a's here, we have 2 a's here. Add the coefficients together, that's 5. then multiply by their like factors, their common factor, a. So 5a, right?
Yeah.
Okay, what about my y's? What should I write?
8y, negative 8y.
Negative 8y. We have negative 5 of them here, we have negative 3 of them here. In total, we have negative 8 of those. And then for my constant, we have negative 8 and 6 is
Subtract 2.
minus 2. Everyone follow that example?
Yep.
Nothing weird?
Nope.
Okay. Next, we're going to talk about the real number line. The real number line. So what is the real number line? We start out by drawing any arbitrary line. There's a random line, right?
Okay.
Now we pick any point on that line, doesn't matter where we pick the line goes off to infinity in both directions, that's what we mean by a line. Pick any random point on that line that we want, and we call that point the origin of our line.
Or 0, right?
We arbitrarily choose to call the origin, we label that with the number 0. Completely arbitrary. Now, the next thing we do is we pick a random length. We pick a random distance. And what do we mean by length or distance? We mean take a line segment, any line segment we want, and we mean that the length of this line segment is what we mean by the distance between 2 points. And whatever we pick that random distance to be, we're going to call our unit. And again, it's completely arbitrary what we choose that distance to be. Do I want it to be this big, this big, this big, this big, this big? Doesn't matter. Just pick something. And whatever it is, we call that our unit. So we pick some distance. I'll pick a distance roughly that big. There's my distance. And I come out and I now make tick marks with that distance on here. Measuring out that many of those distances. So that is our unit for our number line, our unit. And so one of those units, wherever one of those units lands, we call 1. Wherever 2 of those units lands, we call 2. Wherever 3 lands, we call 3, 4, etc. Right?
Yeah.
Similarly, to our left, whatever one of those units to our left, wherever one of those units to our left lands, we call minus 1. Wherever 2 of those units to our left lands, we call minus 2. Wherever 3 of those to our left lands, we call minus 3, etc. So you pick a random origin, you pick a random unit, and then you can start populating your real number line with numbers.
Okay.
Notice that a number makes absolutely no sense without some unit to make reference to. When I say it's 5 to the right, I mean it's 5 of those units to the right. If you ask me, how tall is that bookshelf, and I told you 6, that doesn't tell you anything. How tall is it? 6. You need 6 what? 6 units. If I said, here's my unit, and I said, and it's 6 of those, now you know what I mean. It makes 0 sense without reference to a unit. Make sense?
Yeah.
So then we pick our unit, and we picked our unit to be roughly that, and so we populated the number line. And then we can populate all the numbers in between with fractions of those distances as well. And so for every real number in existence, it's not something we'll prove, one of those things you have to take my word for since it's beyond the scope of this class. For every real number, there's just one and only one point on the real number line corresponding to that number. So any random number in existence you pick, pi square root of 2 over 7. Pi square root of 2 over 7. That's a real number. There's a corresponding value to that many of these units somewhere on this line. I don't know where it is, but somewhere on there, right? Okay, any questions with that? It's a concept that you've come across a lot, but just in case, whenever you flush it out. Okay. Next. Less than and greater than. Notice that thus far, even though we've talked about the terms before, we haven't explicitly used the less than symbol or the greater than symbol. So that's what we're going to define next. So to say that A is less than B, or that B is greater than A, in other words, those two say the same thing. So to say that A is less than B, or that B is greater than A, means to say that b minus a is a positive number. What do we mean when we say a is less than b? We mean b minus a is a positive number. What do I mean by b is greater than a? I mean b minus a is a positive number. That's what it means.
Okay.
So, to say that a is less than b is logically equivalent to saying that b is greater than a is logically equivalent to saying b minus a is a positive number. Alright, let's go through some examples. Is 4 less than 6 or greater than 6?
Less than.
Less than 6. Let's test. 4 minus 6, what is that?
-2.
-2. Oh, I did it backwards, huh? Sorry, here's our b, here's our a. To say that 4 is less than 6 is to say that b minus a, 6 minus 4 is a positive number. So 6 minus 4 is equal to 2. 2 is positive, so yep, that's true. Notice if you try to say it this way, if I try to say 4 is greater than 6, that's saying that 4 minus 6 is positive. But 4 minus 6 is equal to -2. That's not positive. So this is a false statement. This is a true statement. Using our definition. Don't just appeal to the obvious. Make sure it makes sense with your definition.
I actually almost didn't think that made sense. I was about to say, no, that's not true. And then I realized that it's obvious.
Okay, so 4 is less than 6. Alright, let's try another one. Is -3 less than -7? Or is -3 greater than -7? Less than, right? Let's try it. If -3 is less than -7, then that means -7 minus -3 is positive. So let's try that. -7 minus -3. What's minus -3? That's plus 3, right? So this is the same thing as -7 plus 3. What's -7 plus 3? -4. Is that a positive number?
Of course.
No! So -3 is not less than -7. That was a false statement. Maybe -3 is greater than -7. Let's try that. -3, is that greater than -7? Let's see. -7, or -3, minus -7. That's the same thing as -3 plus 7. That's 4. Ah, that's a true statement. So -3 is in fact greater than -7.
Okay.
And hopefully that appeals to your intuition. Do you have more money if you owe me $3 or if you owe me $7? If you only owe me $3, then you have more money. Do you want to owe me $3 or owe me 7? Your choice. Bring the money tomorrow. Okay. Let's try the next one. -10 and 0. Is -10 greater than 0 or less than 0?
Less than 0.
Less than 0? Would you rather have $0 or owe me $10?
That's a tough one.
All right. So let's test it. So you said it's this way. Let's try it. 0 minus -10. That's equal to
-10.
0 minus
Oh,
-10.
0 plus 10.
That's equal to 0 plus 10, which is the same thing as
10.
10. Is that a positive
I
number?
think so.
Yes. So -10 is less than 0. We getting this?
Yep.
Yeah.
Let's try another one. -20 and 1. Is -20 greater than 1 or is -20 less than 1?
Less than 1.
Less than? 20 is way bigger than 1.
No. It's less than.
Alright, let's try it. You say -20 is less than 1, that would mean that 1 minus -20 is positive. Let's see if it is.
Right.
1 minus -20 is the same thing as 1 plus 20.
20.
Is equal to 21. That's a positive number.
I'm
Good.
never ever gonna think of the would you rather owe me or have. I'm forever gonna think of that.
The easiest way to keep track of it in your head, I don't know. Everyone has their own little tricks. On the number line, which number is on the right side? Numbers this way are bigger, number that way are smaller. So always look at which number is on the right side. That's the way I think about it. So 4 and 6, here's 4, here's 6. Which one's on the right?
6.
6. Let's look at the next one. Negative 3, negative 7. Here's negative 3, here's negative 7. Which one's on the right?
Negative 3.
Negative 3. And then negative 10 and 0, here's 0. Negative 10, 7, 8, 9, 10. Which one's on the right?
0.
0. And then finally, we had 1. And then negative 20's way over here. Which one's on the right? 1.
Yeah.
So, whatever helps you think about it, but that's personally the way I always think about it. Anyways, next, just something to note. So by definition, x less than 0, so if I tell you that x is less than 0, by definition, x being less than 0 means 0 minus x is positive, right?
Yeah.
Yeah.
If I know that x is less than 0, that is the exact same thing. Remember, the right side minus the left side is positive. A less than b is the same thing as b minus a is positive. Left less than right means right minus left is positive.
Correct.
Follow that? Okay, so if I say that x is less than 0, that says that 0 minus x is positive. But 0 minus x is the same thing as just minus x, right?
Yes.
So if 0 minus x is positive, that means negative x is positive,
Right.
right?
Okay.
And if negative x is positive, what's x?
A
Negative number.
Negative. So if negative x is positive, x is negative. You with me? Okay. So notice that saying x is less than 0 says the exact same thing as x is a negative number. Being negative and less than 0 mean the exact same thing. You intuitively already knew that. Here's using our actual definition. Follow that?
Yeah.
Alright, once again. If I say x is greater than 0, looking at our definition up here, b greater than a means b minus a is positive. So if I say x is greater than 0, that means x minus 0 is positive. Right?
Yeah.
What is x minus 0?
Just x.
Just x. If I have x and I subtract 0 from it, what do I have left? Just x. Hopefully that's not weird. So, to say x is greater than 0 is to say that x minus 0 is positive, which means x is positive. And so, x greater than 0 and x is positive say the exact same thing. Again, you intuitively already knew that, but I want you to see it from our definition. Good? Okay, next. When we say x is less than or equal to y, that means that x is less than y, or x is equal to y. So, x is less than or equal to y means one of those two statements are true. Question. Is 11 less than or equal to negative 2? No. Is 11 less than negative 2? No. Is 11 equal to negative 2?
I hope not.
No. Okay. So no, that is a false statement. Let's try another one. Is negative 3 less than or equal to 0?
Yeah.
Yes. Is negative 3 less than 0?
Yeah.
Yes. Is negative 3 equal to 0? No. So is it less than or equal to 0?
Yes.
Yes. Remember, with an or, you just need one of the two statements to be true for the whole thing to be true. Right? Okay, let's try another one. Is 0 less than or equal to 0?
Yes.
Yes.
Yes. Is 0 less than 0? No. Let's check that with our definition. Let's check with our definition really quick. Is 0 less than 0? 0 less than 0 would be true if what?
0 minus 0.
If 0 minus 0 is a positive number. Is 0 minus 0 a positive number?
No. Yes.
No, 0 is not positive. And for some reason, kids have a connection with this with even and odds. Has nothing to do with each other, but 0 is even. It's not positive or negative. I don't know why those wires cross, but for some reason they do. So let's make that clear. 0 is not positive, 0 is not negative.
So 0 just is. So 0 is not less than 0.
0 is not less than 0.
0 is
So 0 is equal to 0, but it is not the case that 0 is less than 0. Okay. Yeah, 0 is not positive, 0 is not negative. Similarly, to say that x is greater than or equal to y, it's the same thing as x is greater than y or x is equal to y, and I think you get what that means.
Yeah.
We doing all those?
Yeah.
Okay. Now, operations on functions, or on fractions, not functions. We're still ways away from functions. Operations on fractions. So let a, b, c, and d be real numbers where b and d are not 0. You with me so far?
Yeah.
Okay. We say that two fractions are equal to each other. We say a over b is equal to c over d, provided that a times d is equal to b times c. Now let's see this in action with a couple numbers that we already know, and then hopefully it'll click in your head what that's saying. So question, is we'll do it this way, is 1/3 equal to 2/6?
Yes.
You positive?
Yeah.
Okay, is 1/3 equal to 2/6? Let's check. This says that two fractions are equal to each other, provided that a times d is equal to b times c. So this is equal only if 1 times 6 is equal to 3 times 2. Is this true?
Yeah.
Then this is true. That's what this is saying. Another example? More complex one?
Sure.
Alright, let's look at 3/5 and see if that's equal to, what should we do? 12/20ths? Are those equal? I don't know, let's check. We need to see if this times this is equal to this times this. 3 times 20, is that equal to 5 times 12?
Yeah.
3 times 20 is?
60.
5 times 12 is?
60.
They're the same. Therefore, these two fractions are equal. Let's try another one. -3/5 over 12 and 12 over -20. Are those two equal?
Yeah.
You sure?
Yeah. Yep.
Let's check. How do we know those two are equal? We need to see if -3 times -20 is equal to 5 times 12. What's -3 times -20?
Positive 60.
Positive 60. Remember, an even number of negatives gives us a positive. That's still 60 is equal to 60. It works. Right? What if I were to move the negative sign up here? What do you think? Still equal?
Yes.
Yeah.
Yeah, no, maybe?
Yeah.
Yes.
Definitely. -3 times 20 is -60. 5 times -12 is -60. Those are the same, so those two fractions are equal.
Yep.
So that's what we mean when we say two fractions are equal. Good?
Yeah.
Again, we could have proved this from what we did last time. Remember that from the axioms I gave you guys, before we started the book, we came up with the definition of division. We could have proved this. The author is just going to introduce you to these as properties of fractions. He's not proving these to you, he's giving these to you as what we mean by fractions. We could have proved them from those earlier axioms that we started with, but the book's not going to do that. You understand what I'm saying?
Yeah.
So they're given to you as properties rather than as things that we're proving. So in the book, these aren't theorems, these are definitions by what we mean two fractions being equal means. Two fractions being equal means this. How do we multiply two fractions? Like this. How do we add two fractions? Like this. So he's given these as properties, not proofs. Let's make sense of the next one. Alright, how do we multiply two fractions together? So if I have a fraction like 2/3 times 4/5, according to the author, the way I multiply these two fractions together is I take the two terms in the numerator, multiply them together, and I take the two terms in the denominator and multiply them together. So this is the same thing as 2 times 4 over 3 times 5. And 2 times 4 is?
8.
3 times 5 is?
15.
And there we have it. So that's how we multiply two fractions together. Good?
Mm-hmm.
Next, how do we add two fractions together? So we'll do 2/3 plus 1/4. Now, the way that you've been taught to do this in the past is what? Get a common divisor, right? Get a common denominator.
Yeah.
Yeah.
So to get a common denominator, I need to multiply this one top and bottom by 4, and this one top and bottom by 3, and it will do that.
Yeah.
So let me rewrite this so I have a little bit more room. And now I'm going to show you that we're doing the same thing here. So 2/3, I can't remember what I added, 1/4?
Yeah.
Okay, that's equal to, if I multiply this term by 1, I don't change it, right?
Yeah.
So I'm going to rewrite this term as 1 times that term, and we didn't change it. 1 times 2/3, right? Plus, I'm going to multiply this one by 1. You with me? And so now what do we get? We've got 4 times 2, which is 8 over 12, plus 3 times 1 is 3 over 12, which is equal to, I'm going to write it this way, 8 plus 3 over 12. You with me? Okay, now let's just do it blindly looking at his formula that he has written here.
Okay.
Redo the same thing. So I'm doing 2/3 plus 1/4. So 2/3 plus 1/4. And he says that's going to be, it's going to be equal to, we have a times d, so this term times this term, which is 8, right? A times d, which is 8,
Yep.
plus b times c, which is 3, all over b times d, which is 12. You follow that?
Yeah.
So get the same thing. So here's the shorthand for it. If you're doing a over b plus c over d, there's your formula. And it does exactly what you would have guessed you should do with a problem like this. Getting a common denominator. Any questions on any of those? No? Okay. Let's move over. Keep shifting too much. And we're getting roughly. Go past that. Okay. So next thing we're going to prove. We're going to prove if we have three numbers, a, b, and k, so if a, b, and k in the real numbers, or if a, b, and k are real numbers, where b is not equal to 0 and k is not equal to 0, then a divided by b is the same thing as k times a over k times b. In other words, if you have a fraction, you can multiply the top and bottom by the exact same thing, and it doesn't change the fraction. That's what we're going to prove real quick.
Okay.
With me on what we're proving?
Yeah.
Yeah.
All right, so let's start. Remember, if you're trying to prove an if-then statement, you assume the antecedent and show that implies a conclusion. So assume the antecedent. Let a, b, and k be real numbers such that b is not equal to 0 and k is not equal to 0. The if part of this statement. Good?
Yeah.
Now, observe that a times k times b is the same thing as b times k times a. We know this from commutativity and associativity of multiplication. I just reordered my a, my b, and my k and grouped my terms a little bit different. But you agree that these two are the exact same thing, right?
Yeah.
Yeah.
Okay, now look at our definition for two fractions being equal. For two fractions being equal over here, a over b is equal to c over d, provided that a times d is equal to b times c. So since I have a times d is equal to b times c, I have a over b is equal to c over d. This is acting like the d, this is acting like the c. In our definition.
Yeah.
So this says the exact same thing as this. if you look at our definition right here, might take a little bit to see it, but once you see it, it's there. A times D is equal to B times C gives us A over B is equal to C over D. Everyone see that? And there we go. So we just proved it. Since that's equal to that, that's equal to that, therefore, when you multiply top and bottom of a fraction by k, you don't change the value. It's still equal to the same value you started with. Good? Any questions? Okay. Now what about dividing the top and bottom by k? The author didn't show this, so I just wanted to show it really quick as a side note to show you you still get the same thing. All right, so A over B, if A over B were equal to A divided by K over B divided by K, then what would that mean? That would mean that A times this is equal to B times this. So that would mean that A times B divided by K is equal to B times A divided by K. Looks a little weird since I'm changing symbols here, but I'm just using this property again. I'm saying that this means the same thing as this. Where this is my A, this is my B, this is my C, this is my D. I'm doing A times D is equal to B times C. The only difference is instead of writing A divided by K like that, I wrote it A divided by K like that. Doesn't change anything.
Yeah.
And instead of writing B divided by K like that, I wrote B divided by K like that. We still have A times D is equal to B times C. Everyone good with going from this to this? Just using that again. Okay. Now, something that we talked about when we said that, well, I think you'll just see it. A is the same thing as A divided by 1, right?
Yeah.
And B is the same thing as B divided by 1. That's my only difference going from here to here. Good?
Yeah.
And now we know how to multiply two fractions together. If I have a fraction times a fraction, that means multiply the numerators together, divided by multiply the denominators together. So A times B is just A times B, 1 times K is just K. B times A is just B times A, 1 times K is just K. So this being true is the same thing as this being true, is the same thing as this being true, is the same thing as this being true. Now, is this true?
Yeah.
How do we know that this is true?
Say,
Commutative property of multiplication. If I want to write this out one more way, I could rewrite this as, I can keep this term the same, and I know that multiplication is commutative, meaning I can change the order of my terms and it doesn't change anything. So I have identical symbol equal identical symbol. That's always true.
What if A and B were positive and negative numbers? Like A was
We
positive.
know nothing about, they could be positive and negative. We know nothing about them.
But if that were true, then that would be wrong.
It doesn't change anything. Pick any value you want for A and B, and this is true. We'll plug in whatever numbers you want here in a second. Let's follow the backtrack, and then we'll plug in some numbers and see it. So A times B over K equals A times B over K. This is always true. I have some symbol equals some symbol. That's always true. Right?
Yeah.
And since multiplication is commutative, I know this being true means this is true. And we're just going backwards from our same logic here. This being true means this is true. This being true means this is true. This being true means this is true. So this is true. Because that's the same thing as that, is the same thing as that, is the same thing as that, is the same thing as that is true. Therefore, what we started with is also true. So this statement's true. Now you said, what about if A and B were positive, or one's positive, one's negative?
I was thinking about addition. I just realized.
Yeah, this is true for any numbers A and B and K, as long as B and K aren't 0. That's our only exception. And it doesn't matter what three numbers you pick, this will be true. I don't know, do we need to see an example of that? Do you have three numbers you want to test? Or is it obvious to you that's true?
It's obvious.
It's obvious? Okay, then we'll just go on to whatever numbers I already picked here, because it looks like I have an example. Okay, So 5 over 7, we're then saying is the same thing as 3 times 5 over 3 times 7, which is 15 over 21. So 5 over 7, we're saying is equal to 15 over 21.
Yeah.
Now, is that true?
Yeah.
We know how to check if that's true. What does it mean for this fraction to be equal to this fraction? It means that times that is equal to that times that. We can test that. So is 5 times 21 equal to 7 times 15? Is 5 times 21 equal to 7 times 15? Let's see, what is 5 times 21?
105.
105. And what is 7 times 15?
105.
Are you just saying that, or did you actually think about it?
No, I thought of it.
5 times 20 is 100. So 5 times 21 is 100 with one more 5.
Yeah.
Right?
Yeah.
7 times 10 is 70. 7 times 5 is 35. 70 plus 35, 105.
Yep.
Checked your calculator, came out?
No.
Alright, so 105 is equal to 105. Therefore, 5 times 21 is equal to 7 times 15. Therefore, 5 sevenths is equal to 15 21s, or 21st. Good? Let's check the next one. An example, this time we're dividing the top and bottom by the same thing. So I start out with 36 over 48. And now I'm going to divide the top and bottom by 12. 36 divided by 12, that's 3. 48 divided by 12, that's 4. Is it true that 36 over 48 equals 3 times 4?
Yeah.
We can check that.
Just divide it by 12.
We need to check if we're proving that you can do that. You can't use your proof in your proof. Well, we're not proving it, we're getting intuition for it. I guess you could use it since we proved it, but we want to get intuition for the fact that this works now. We should have done this before we did our proof. 3 times 48. So, let's check that. 36 times 4, what is that? 30 times 4 is
120.
120. 6 times 4 is
24.
120 plus 24 is
144.
144.
It's just 12.
That's just 12 times 12. Exactly. That's another way that you could have thought about this if you want. You could have said 36, that's the same thing as 12 times 3, right?
Yep.
So this is 12 times 3 times 4, since 36 is 12 times 3. And now you can think about 3 times 4 is,
12.
times 12 is
144.
144. So whichever way helps you think about it.
Yep.
Once again, looking at this one, 3 times 48 is, well, let's see, what's 3 times 40?
120.
120. What's 3 times 8?
24.
120 plus 24 is
144.
144. So it is in fact equal. So since this is equal to this, then this fraction is equal to this fraction. And it worked.
Can you give us an example where it doesn't work?
No, because it always works. We proved it always works. So these examples were just to help cement it into your intuition what it was we were talking about. Well, I can give you an example where it doesn't work, but I'd have to cheat. And I'd have to either make b equal to 0 or k equal to 0. Then it wouldn't work. Because then it wouldn't even make sense why I wrote it. Because you'd be dividing by 0. Okay. Next. How do you divide two fractions now? Okay, so if we do a divided by b, if we do a divided by b divided by c divided by d, or a over b divided by c over d, probably a clearer way to say that, what does that equal to? Now you might have memorized the rule. If I take one fraction and I divide it by another fraction, that's the same as taking the first fraction and multiplying by the reciprocal of the second fraction. You know what I mean by reciprocal of a fraction?
Yeah.
Flip the numerator and denominator. So, we're saying it's equal to that times that over that times that. A times D over B times C. And we're going to prove that. But that's the way that you were taught it back in school. Maybe this time do an example first and then go into the proof. So we're saying, for example, if I have 4/3 and I want to divide it by 1/2, how do I do that?
You flip 1/2. Get the reciprocal 1/2.
Then this is the same thing as 4/3 times 2 over 1, right?
Yep.
Which is 8/3, that's the way that you were taught in school?
Yeah.
So that's what we're going to prove here. So A over B divided by C over D, we're going to show is A times D over B times C. Okay, so let X equal the solution to this equation.
Okay.
Now we have our definition for division way over there in the second column at the top. If X is equal to a term divided by a term, that means X times the second term is equal to the first term.
Yeah.
That's what we said in this definition. To say that X is equal to, we didn't really write that X is equal to B over C over here. We just went straight to this, but don't really have somewhere to write it. We don't really need this anymore. So to say that X is equal to B divided by C is the same thing as to say that B is equal to C times X. These two things are logically equivalent. You with me? Now let me write it with the divide symbol in there, the way that we have a divide symbol in there. If I say that X is equal to B divided by C, that's the same thing as saying that B is equal to C times X. You with me?
Yeah.
So now, looking back over here, since X is equal to, from our definition, B divided by C, that means X times C is equal to B. Looking at our definition over there. Everyone follow how this says the same thing as this?
Yes.
Nothing weird there? Okay. Now, what am I trying to show? I'm trying to show that X is A times D over B times C. Right? I'm trying to show that A over B divided by C over D is this. So I said let X be that thing. I'm going to show that X is in fact this. Since X is that, if I can show that X is also this, then we're done. Because then these two things are equal.
Yeah.
You with me? Okay. So, X is the unique number that makes this statement true. If I can show that this number also makes this statement true, then X has to be this number. That's the logic there. So I'm going to show that if I plug in this number for X, it makes the statement true. And therefore, X is that number. And since X is this, then X is also that. Or then those two are equal, I mean. You follow the logic there?
Yeah, gotcha.
Okay. So observe that. So if I replace X with this thing, A times D over B times C. So all I can do is rewrite this equation, but plugging in this value for X.
Right. Well,
Oh.
yeah, you just did A times D over B.
Let's see, what did I do?
A times D over B times C is X.
A times D over...
B times C is X. And then you
Oh,
just-
okay, yeah. I didn't plug in, ignore this side of the equation.
Yeah.
So I'm just going to take X, I'm going to replace it with that here, and I'm going to see what we get. So I'm rewriting this right there, I'm just going to see what that's equal to. And hopefully it comes out to that.
Yeah.
That's what we're hoping for. So I'm going to start here, I'm going to rewrite it and see what that gives me. So X times C over D, so I take X, I replace it with this, and we're going to see what we get. So A times D over B times C over D is the same thing as, I can rewrite these terms in any order I want. So we had an A, a D, and a C in the numerator. I decided to write it as A, C, D. Just change the order, right?
Yeah.
Since multiplication is commutative, we can change the order. Similarly, in the denominator, I had B times C times D, so I'm just going to write it as B times C times D and keep it in the exact same order. You with me? Now, A over B is still just A over B. What's C over C?
1.
What's D over D?
1.
So it comes out to just A over B. So since I showed that this number times C over D is A over B, then this number is X. Because X is a unique number, such that when you multiply it by C over D, you get A over B. I showed that this times C over D gives you A over B. X is a unique number, such that when you multiply it by C over D, you get A over B. Therefore, this number is X. So we let x be this, and we found out that x is also this. Therefore this and this are equal. Therefore that is the same thing as that. You follow the logic there?
Yeah.
Could be a bit of a mouthful, but it's real simple. So once you get it, it's one of those things that once you get it, it's obvious, but until then, sounds like I'm saying a lot of things. Okay, and that finishes off this section, I think. So then we're off to our first group of exercises, and I guess none of you really have the book, huh? Because then I'd let you guys just pick random exercises that you wanted to see me do. Were you here for the first lecture?
Sorry.
Go watch the first minute of the first lecture, first 5 minutes of the first lecture, and you'll have all the information about the book that you need. Go get it. Let's pull that closer. So I'll just start randomly picking problems. Let's see. We got numbers 1 through 68. You guys can randomly pick a number, and we'll solve that one. Huh?
56.
As a general rule, it's good to start out lower and work your way up higher and do them in that kind of order. But we can just jump to 56 if you want. It just probably won't follow the flow of the lecture. 6? I heard a 6.
Yeah, I said 6.
All right, 6. 6 we have. 6, all it tells me is -2, 8a, minus 3b, minus c. And let's see what the instruction is for this whole group. Compute the expression if possible, otherwise remove any signs of grouping and collect similar terms. So basically, simplify this as much as we can, is all I'm saying.
Okay.
You with me?
Yeah.
So first thing we need to do is distribute the -2 inside of here. So I need to apply -2 to every term inside of here. So that's the same thing as -2 times AA plus -2 times -3b plus -2 times -c. Take every term in here and multiply it by -2.
Okay.
Everyone follow what I did there?
Yeah.
Nothing weird?
No.
Okay, and what is -2 times AA?
-16a.
-16a.
Plus.
Anything weird there?
Nope.
Is that okay that I did that? There wasn't an a term here. Can I multiply two terms together if they don't both have a's?
Yeah, but you're just not adding them.
Yeah, it's when you're adding them that you need to keep track of if they have common factors. So you can multiply terms together that don't have common factors. That doesn't matter. It's when you're adding them together that we care. Okay?
Okay.
So that's -16a. What do we get from this one?
6b.
Yeah, -2 times -3 is 6. And then multiplying by b is still just b.
Plus
And then plus
2c.
2c. Wonderful.
Okay.
All right. What one next?
12.
12. 12 gives us -2b minus 6 minus 3b minus 4. Good? All right, we'll do this the slow way. As a general rule, distribute your negative on your innermost parentheses first, and then work your way out.
Okay.
So I'm going to rewrite this as -2b minus 6, and I'm going to distribute this negative through. So negative times 3b gives me
-3b.
-3b. Negative times -4 gives me
Positive.
4.
+4. Follow me on that?
Yep.
Yep.
Okay, next we'll distribute the negative through these parentheses. So I'll have -2b, -6 gives me
-6.
-6, negative -3b gives me
3b.
+3b, negative +4 gives me
-4.
-4, right?
Yep.
And then finally, distribute to our last negative. Negative 2b gives me,
Negative 2b.
just tell me.
6.
Plus 6 minus 3b plus 4.
Good. All right, give me another number.
18.
18. Write in a line the sum. Oh, they spell it out as words to make sure that you can go from the words to writing it on paper. So that's not a great one to do since I'd have to write it up there for you guys to do it.
Okay.
19. Construct a real number scale. Read the inequality. Check it by use of 1 on page 14. 1 on page 14, which means to check that their difference is positive. And verify the inequality on your scale. And 19 is 5 is less than 9. So 5 is less than 9, that's what we're validating. So 2 ways it wants us to validate it. First, it wants us to check that the right minus the left is positive. So what's 9 minus 5? 4. Is that a positive number?
Yes, sir.
So it's true that way. The second way they want us to check it is on a real number line. Here's 0. 1, 2, 3, 4, 5. Here's 5, 6, 7, 8, 9. Here's 9. Is 9 to the right of 5?
Yes.
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 Voila.
Voila. Alright, next.
24.
24. Decide which sign should be applied. I have negative 5, I have negative 9. Should I do greater than, or a less than, or an equals?
Greater than.
Greater than? You're saying like this?
Yeah.
Yes, sir.
You sure?
100%.
Yep.
Let's check it. What's negative 9 minus negative 5 equal to?
4.
Negative 9 minus negative 5 is equal to what?
4.
Negative 4.
Negative 5. Negative 9 is
I
5.
think you're supposed to go negative 5 minus negative 9.
Oh, did it backwards, huh? Because my sign's this way. Negative 5 minus negative 9. Negative 5 minus negative 9. Okay, what's that equal to?
4.
4. Ah, don't blindly just follow what you think an equation is. Good. Alright, next number. Huh?
30.
30. Divide to express a rational number as a repeating decimal. We didn't go over how to do that.
Sounds like fun. Seems like a math.
Wait, yes we did. We did last class.
We didn't go that way. 7 over 12, you just have to do the division. Express 7 over 12 as a repeating decimal.
Can
Is what we're doing.
Can we use calculators then?
Can you use calculators? You don't need to use a calculator.
What do you mean?
This textbook presupposes that you don't use a calculator. This textbook is old enough that the notion of a calculator didn't exist. Or it would have been absurdly massive, like this classroom big. So, no, it presupposes that you can't use a calculator, and you'll notice at the end of the book there's a bunch of tables for looking up certain operations, like taking a logarithm. So no, he expects you to be able to do this without a calculator. Okay, so how do we do this? 7 divided by 12. Well, this goes back to long division, the way that you know and love, right?
Yeah.
So we're doing, what goes right here?
12.
12, and we're dividing it by 7,
Right.
right?
Right.
Yeah.
Oh.
Yeah.
No.
Yeah.
You guys know how to write out long division?
To the right, so 7's inside.
Thank you.
Yeah.
No.
John has it right.
12, 7. That's how you write it.
Okay.
You're so used to putting the bigger number there without ever thinking about it.
Yeah.
Sanity check really quick. Let's do 7, 12 like this. Let's assume we write it like that. What do we get? How many times does 7 go into 12? 1 time. 1 times 7 gives us 7. Minus gives us 5. Bring down to 0. How many times does 7 go into 5? 7. And we get 1.7 da 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 da. But we got a number bigger than 1. Is 7/12 bigger than 1?
No.
No! Sanity check. Wrong. Bad. Okay. So it's like this, right?
Right.
Okay, how many times does 12 go into 7?
0.
It doesn't. 0. Okay, so then we add on our 0 place. Now how many times does 12 go into 70?
5.
5 times. What's 5 times 12?
60.
60. Subtract, we get 10. Bring down another 0. Because remember, we can think about 7 as 7.00, as many zeros here as we want, right?
Yeah.
Okay, so we bring down our 0. Bring down our 0 now. How many times does 12 go into 100?
8.
8. What's 8 times 12?
96.
96. Subtract. What do we get?
4.
3.
4. Bring down our 0. How many times does 12 go into 40?
3.
3 times. 3 times 12 is
36.
36. Subtract is
4.
4. Bring down the 0. How many times does it go in?
3.
And we're going to get that again, and again, and again, and again. Right?
Yeah.
So once you find the repeating pattern there, you stop. And so 7/12 we can re-express as 0.583.
Yeah.
And that's how you do it. No real trick to it. You just take the bull by the horns.
That would be funny if someone just kept doing it. Just kept solving for 3.
Yeah, hopefully you can induce the pattern from that. So, yeah, glad you guys picked that one, because we didn't cover that. Okay, what's next?
36.
36. Express the results by use of a fraction in lowest terms. Okay, so we're trying to write -3/12 in lowest terms. What's that equal to?
1/4.
1/4. But let's try and go through the steps here to figure out how we come to that using our rules. I know I can multiply the top and bottom by the same thing, right? So I'm going to multiply top and bottom by -1. And what does that give me? 3/12, right? Multiply that by -1, we get 3. Multiply that by -1, we get 12. I can also divide top and bottom by the same thing. So if I take the top and bottom and I divide them both by 3, let's see what I get. 3 divided by 3 is?
1.
12 divided by 3 is?
4.
You sure?
Yeah.
All right. So we get 1/4. Let's do another one like that. So 37. -78 over -26. Because you guys picked the easy one. -78 over 26. Negative. You with me?
Yeah.
Yeah.
Okay. So what's the first thing we're going to do?
Get rid of the negatives.
Now let's get rid of this negative right here. How can we get rid of that negative?
By blending it with that line. I'm just kidding.
No, well,
Let's think about what that negative is. That's the same thing as -1 times 78 over -26, right?
Yeah.
You good with that?
Yeah.
And I can also view that -1 as just, we'll do this really slow one time and then we'll never do it this slow again. Right?
Yeah.
Good with that? Now we know how to just multiply it in. So -1 times -78 is
-78.
-78. And 1 times -26 is
-26.
-26. The short way of saying that is anytime you have negative some fraction a over b, it's always the same thing as just applying the negative to the numerator. Negative a over b. You can always take that and just apply it to the numerator.
Okay.
Going through this exact process.
Yeah.
Good?
Yes.
Okay, that's what I meant by I'll do it that way once, never again. Okay, so now we've got it written like that. What should we do now?
Times it by -1.
Times top and bottom by -1, right? Times top and bottom by the same thing. That's using this one. A over b is the same thing as k times a over k times b. So this is equal to, when we multiply this by -1, what do we get?
78.
78. Multiply this by -1, what do we get?
26.
26. Good. Now what should I do?
divided by 2 until you get what you have.
All right, we'll do it that way. So he says, notice, that's an even number, and that's an even number. So 2 has to go into both those numbers.
Right.
So I'm going to divide this one by 2, and I'm going to divide this one by 2. I'm going to divide the top and bottom by 2. Remember, that's one of our rules. A times B is the same thing as A divided by some number over B divided by some number, as long as we divide by the same number. So I'm going to divide the top and the bottom by the same numbers. So what is 78 divided by 2?
39 and 13.
39. And 26 divided by 2? 13. Right?
Mm-hmm.
Okay. Now what?
13 is prime, so that's done, right?
13 is prime, so that's done.
Ta-da!
Ta-da!
Mixed numbers.
13 goes into 39.
Yeah, 13 goes into
Yeah, not so fast, buddy. That's not prime.
Yeah.
So this is the same thing as the numerator divided by 13 divided by the denominator divided by 13. So 39 divided by 13 is,
3.
that's some quick math. 13 divided by 3 is,
1.
that took you longer. Oh, did I say divide by 3?
Yeah.
13, yeah, I often say the wrong thing. Don't let me do that.
13 divided by 3. 1.
Okay, so, and then that's equal to
3.
just 3. There we go. Alright, next number.
42, I guess.
42. The answer to life, the universe, and everything. Express a result by use of a fraction. Oh, still same thing.
We could go to 43.
So,
You know there's a whole cult around that. 42?
42.
Deal.
Huh?
So have you read Hitchhiker's Guide
Yeah,
to
I know
the
that's
Galaxy?
the reference.
Okay.
Just thinking of cold.
Yeah, it's a big deal.
Alright. So we have 8/15 divided by 2. What are we going to do?
Divided by 2.
8/15.
2 can be wrote as 2 over 1.
Perfect. We can rewrite this as 8/15 divided by 2 over 1.
Meaning we take the reciprocal of 2 over 1.
Now, we can use this. A over B divided by C over D is the same thing as A times D over B times C. So this is equal to A times D over B times C. You follow that?
Yep.
Or another way we could write it, if you're more comfortable with just writing it this way, that's the same thing as 8/15 times 1/2. Dividing by 2 and multiplying by 1/2, same thing. Right?
Mm-hmm. Yeah.
Okay? And that's equal to
8/30.
8/30ths.
How is that 1/2 of 8/15?
Good.
I don't understand the question. 8/15 divided by 2 is the same thing as 8/15 times 1/2.
Right, so 8/30ths is 1/2 of 8/15.
Right. Isn't that what we said?
Yes, I'm confused. How is that half of 8/15?
How is 8/30ths half of 8/15?
That just doesn't make sense.
Yeah.
You'll see it here in a second on this next step. Okay, so we take the Chandler approach. We say that's even, divide top and bottom by 2, right?
Yeah.
So that's equal to, what's 8 divided by 2?
4.
4. What's 30 divided by 2? 15. Ah, what's half of 8/15? 4/15.
What? Oh, well, duh. Okay.
Well, duh, okay. That's what we love to hear. Means it's clear.
Shoot, that was funny.
Good?
Yeah.
Nothing weird there?
Cool.
Alright, what's our next number?
We do the lucky 56 now? 48 to 48.
Oh,
48. Oh my goodness, she writes improper fractions.
We're just going by 6s to just get the basis of it.
4 times 5/9 divided by x over 3. So we're rewriting that. Okay. So, Except that's not a times. I don't know. That's why I hate improper fractions. I think he intended this as an improper fraction. Maybe he doesn't. Now I forgot what number it was. 48? I doubt it. I doubt he means that as an improper fraction. I think we're just saying 4 times 5/9 divided by x over 3. Okay. So let's work this one out. What should we do first?
You could write 4 as 4 over 1.
Alright, so this whole thing is equal to 4 over 1 times 5/9 divided by x over 3.
Which is 20 over 9 divided by x over 3.
So now we know how to multiply the fractions together. So 4 times 5 is 20. 1 times 9 is 9. And we're dividing that by x over 3.
Take the reciprocal of x over 3. Or we could just...
So this is equal to 20 over 9. If we divide by x over 3, that's the same as multiplying by 3 over x, right?
Yeah.
Yeah.
Okay, and what's that equal to?
60 over 9x.
Okay. 60 over 9x. And what's that equal to? Or are we done?
Not,
No. It's...
Are they both even?
yes.
No, but we can divide by 3.
No, but they're both multiples of 3.
Right.
Okay, so we can divide top and bottom by 3.
20 over 3x.
So 20 over 3x. Now are we done?
Yes.
It's pretty much as far as you can go.
Pretty much.
Pretty much? Hedging your bets? Yeah, it's as far as we can go.
That's where I put my money.
Alright, what's next? 54? Okay.
Yeah.
This one we have 12a over 5b all over 8a over 15. Right?
Okay.
So, what can we do?
Well, we can rewrite it as like in the division problem, like without the fraction. Like rewrite
You mean introduce this symbol?
Yeah.
Yeah, not gonna do that. Hate that. So I'll avoid it as much as I can. So we have a fraction divided by a fraction is the same thing as a fraction multiplied by the reciprocal.
Yeah.
So this is 12a over 5b times the reciprocal of this, 15 over 8a. After today, I'll never use that symbol again.
Okay.
Okay. So now what should we do?
Multiply.
Multiply?
Or cross cancel.
Cross cancel. Should we introduce the notion of cross canceling?
Yeah.
Okay, cross canceling. We have a 5 here, and we have 3 5s here, right? So I can cancel out top and bottom. I can cancel out a 5 from the top and the bottom. That's the same as, I'm going to divide the top by 5, and I'm going to divide the bottom by 5 really quick.
Yeah.
Okay.
So when I divide the bottom by 5, that's the same as just getting rid of that 5, right? When I divide the top by 5, we can take it out of this, leaving us with just a 3. Good?
Yeah.
Okay, now what?
You've got the A's.
Take out the a's. We can cross cancel out the a's. That a crosses out with that a. We divided top and bottom by a just barely. That's what we mean by cross cancel. Now what?
There's 6 2s and 12 and 4 2s and 8.
There's 6 2s and 12 and 4 2s and 8.
Yeah.
Let's just multiply them out real quick before we get any messier. But I think we're saying. So 12 times 3 now is 36 over b times 8 is 8b. Everyone follow that?
Yep.
Okay.
Will you help me understand why this cross canceling is okay?
Because we divided top and bottom by the same number.
These
So-
people don't say the same thing again.
Just simplify.
If I have 15 over 5, for example, that's the same thing as 5 times, we'll write as 3 times 5. 3 times 5 over 5. And now, that's the same thing as 3 times 5 divided by 5 over 5 divided by 5, which gives me 5 divided by 5 is just going to be a 1. 5 divided by 5 is a 1 times 3 is 3. That would have been the same thing as if right here I would have just canceled out top and bottom 5s.
Yeah, I understand why you can do that. I don't understand how you can cross cancel across the multiplication sign.
Oh, so you're saying, so we have something like 3/5 times 5/3, and then crossing out like that. Multiplication is commutative, meaning I can change the order, it doesn't change anything. So I can change the order on the numerator and write this as 5 times 3 over 5 times 3.
I did. Okay.
And then does the same thing.
Yeah.
Alright, good.
Thank
Any
you.
other questions? Oh, we're not done yet. So we have 36 over 8. And what rule do we apply?
My rule.
The Chandler rule. They're both even,
18
so
over 4b.
we divide top and bottom by 2. 36 divided by 2 is 18. 8 divided by 2 is,
4b.
and we still have our b. Okay, now what?
9 over 2b.
They're both even again, so divide the top by 2, we get 9. Divide the bottom by 2, we get 2b.
That's as far as we can go.
And that's as far as we can go.
Yeah.
Alright, next.
56.
56.
That's not 6.
5 divided by 7 divided by 6.
It's fine, I have to be here.
The factor of 6.
And you need to pay attention to how he draws the lines on here. He writes it as 5 divided by 7 divided by 6. And after this, just for the fun of it, we're going to do 5 divided by 7 divided by 6 and see the difference. But 5 divided by 7, so 5/7 divided by 6, what's that equal to?
Well, we could say 5/7 divided, or times 1/6.
Yeah, we can rewrite this as 5/7 times the reciprocal of the denominator. What's the reciprocal of 6?
1/6.
1/6. This is 6 over 1, so we rewrite it as 1 over 6. Okay? And then that's equal to
5 over 42.
5 over 42. Okay, now let's try this one. So this one we have 5 divided by 7 over 6. What's that equal to?
5 over 1 times 6 over 7.
5 over 1 times 6 over 7, which is equal to
37.
30 over 7, which is not the same thing as this.
Yeah.
You see how those are different?
Yep.
So crucial, pay attention to where your divider takes precedence. And in the book, he does a heavier line, so he doesn't do it longer like I does. He does a lighter line and then just a thicker line for where you're actually doing the divide.
Yep.
So he makes this one dark and then that one lighter. And that's how he specifies that. So for those of you doing homework problems, make sure you don't get that confused, because that can be confusing. All right, what's next?
Number 54.
54,
58.
58.
We did 54.
3h divided by k, all divided by 6. So we have 3h divided by k, all divided by 6. Try and tell it to me just in one go.
3h over k times 1/6. 18h over k. Wait, what?
18h over k.
Huh.
No, it's not 18h over k. Try again. Get it all in one go. See if you can do it all in your head.
Oh, 3h over 6k.
No. Try and get as simple as you can all in one go.
Oh, hang on. Is it
Okay, take it longer
1
than I
over
thought.
2k? 1h over 2k? So h
There
over
you go.
2k.
H over 2k. So 3h over k, we can rewrite this as 3h over k, and rather than dividing by 6, we multiply it by 1/6, right? Now we can cross cancel. We take a 3 out of this, which leaves us with 2 to cancel out that, which leaves us with h times 1 is h, k times 2 is 2k.
Yeah.
H over 2k. Good?
Yep.
All right, what's next?
22. We did.
What? 22? 22.
Other words.
-3 less than 8. We're validating that. How do we validate this? We check if 8 minus negative 3 is positive. What's 8 minus negative 3? 11. Is that positive?
Sir.
Yes, so that's valid. Second way we check it is on a number line. Set up our number line. Here's 0. 1, 2, 3. Here's negative 3. 1, 2, 3, 4, 5, 6, 7, 8. Here's 8. Is 8 to the right of negative 3?
Yes.
Okay, and it's good. Next.
60.
60?
Yep.
60. 6 divided by 3 halves. What's that equal to?
3 over 12 is 1 over 4.
1/4? You guys gonna agree with that?
Yeah.
Yeah. I am.
1/4? If I take 6 and I divide by 3 halves, I'm gonna get 1/4?
Yes, you are.
That's 9.
What do you say? I hear 9. Okay, let's try to answer again. 1/4, I heard 9.
Did you say 9 is in no? Or did you say 9?
What else? Anyone else got a number that they want to throw out there?
I think it's 1/4.
Maybe a 4. Okay, yes, the answer is 4.
No.
Let's see. 6 divided by 3 halves is the same thing as 6 over 1 times 2/3, which is equal to 12 over 3, which is equal to 4 over 1, which is equal to 4.
Oh, I did 3 over halves times 1/6.
3
Well,
over
you're
halves.
wrong.
3 over 2. 3 over halves.
See, I did it like in the right order, but then I did my math wrong. Like I was like 12 divided by 3 is 1/4.
Let's see, common question. What's 10,000 divided by 1/2?
5,000.
5,000, right? No, what's the answer?
20,000?
20,000.
Oh yeah.
That's a
Oh,
common
right,
type of
right.
question. That's going to be asked on like a simple logic quiz. They'll ask you, what's 10,000 divided by 1/2? And everyone says, 5,000. No, that's 10,000 times 1/2 would be 5,000. We want 10,000 divided by 1/2, or in other words, 10,000 times 2. Let's go back to, with our axioms, let's go back to our axioms and think about how we define divided by, and maybe that will help. Going back to our axioms, when we said A divided by B, we said that this is the same thing as A times B's multiplicative inverse. That's how we defined it. So pick a number here, 10,000 for A, divided by 1/2 is the same thing as 10,000 times the multiplicative inverse of 1/2,
Which is 2.
which is 2,
Which makes sense.
which is 20,000. So that's the way that I personally think about division, is multiplying by multiplicative inverse. But whatever helps you think about it. Alright, you want to do any more of these? The last one's 68, so can't go a number higher than that.
Let's do it.
68?
Is there any instance where division can't be thought of as inverse multiplication?
No. Anywhere where it's defined, it can be defined this way. That's a valid definition for division. It's just not the definition that the author chose to use. You can use this as your definition and show that that implies that this statement is true, or you can use this as your definition and shows that that implies this statement is true. Logically equivalent. So I personally choose to think about that way, but it's not how the author does in his definition. Okay, any other numbers?
Can I ask a
Oh.
question?
Go ahead.
It's tangential. It's just, I'm very random
Okay.
thinker. Will you explain imaginary numbers to me?
Sure.
Because I don't know how often I can come, and there's some burning questions I have, and I want to get this one out of the way.
So the best intuition to give for imaginary numbers is to think about the transition to accepting negative numbers. So if you go back to the Greeks didn't have a notion of a negative number. Because anytime they thought about quantity, they thought about it geometrically. I can think about 3 as a line segment with length 3. This is a 3 units long. That's how the Greeks would have thought about 3 as a physical line segment. And so if you would have come to a Greek and you said, and you were just trying to talk to them about a quantity like negative 3, they would have rejected and said, no, there's no such thing. You can't show me a negative thing. You can't show me a negative quantity. And so there was this, I don't know what you want to call it, this rejection of a notion of a negative number for a long time, just because we couldn't come up with some physical way of representing it. Now we use negative numbers all the time, for example, in representing debt. Is a common way that we talk about negative numbers. If I pay you $100,
Is that
then we
historically true? Because they're pretty sophisticated people. I have a hard time accepting that.
the Greeks had no notion of a negative number.
Is that actually true?
Yes, they also didn't have a notion of a number being irrational. But
Which makes sense.
yeah, they thought about what is a number. It's any fraction any positive fraction you can represent as an integer over an integer, and that's what they viewed as all numbers. So they limited themselves to positive rational numbers, and they had no notion of a negative number.
Is 0 over 0 1?
No, 0 over 0 is not 1.
But it works for every other number.
But I don't understand that
Like
question.
3 over 3 is 1. 2 over 2 is 1.
Oh, yes. As long as the division is well defined, as long as x over x is defined, then it's equal to 1. But division by 0 is undefined. And so you can't say 0 divided by 0 is equal to 1. And it gets you into a lot of trouble if you want it to be something. Think about equations of lines for a second. So if I plot a line, any line that goes through the origin, so like y equals 2x, goes through the origin, right?
Yeah.
And what is the slope of this line? How do we find the slope of this line? We do y over x. So divide both sides by x and we get y over x is equal to 2. Huh? You with me so far?
Yeah.
And if you pick any point on this line, so if I pick the point right here, which happens to be at 1 and 2, and I look at y over x, it's 2. If I were to pick some other point up here over at 2, we would have gone up 4. And if I plug that in for y over x, 4 over 2, it's still 2. If I take any point on this line and plug it into this equation, y over x, then it comes out 2. With the exception of the origin. Because if I plug in 0 over 0 on this line, then we get equal to 2. Which doesn't work. Because another line I have, like y equal to x, that's a one where the slope is 1. Then I can also say, okay, 0 over 0 should now also be 1. Since this line has a slope of 1, and it also includes that point. And so I can do any line through there, and for any slope, since I can make my slope anything, I can make 0 over 0 equal to anything. Go ahead.
So you're on my side with 0
No, 0, division by 0 is undefined. If you try to define it, then you start breaking things like making this make sense, which it doesn't. This makes 0 sense. This makes 0 sense.
Yes, thank you. Thank you. Thank you. Okay, that's done. Now back to imaginary numbers.
Okay, so back to imaginary numbers. So there was a similar stigma towards imaginary numbers that there was towards negative numbers. Because what do we mean by negative number? I said I'm just going to take the number such that when I add it to 3, I get 0. Sorry, that wasn't meant to be anything. That was just like a square. Whatever I can put in here to make 0, that's what I mean by negative 3. And I just define it into existence. What does it have to do with physical things in existence? Physical things in reality? Math doesn't care. Who cares? I'm going to say it's the number that satisfies this. That's what negative 3 is. And so we just define it into existence. In a similar way, when we take the square root of numbers, if I say what's the square root of 25, then everyone's happy with that. They know what to do when you take the square root of a positive number. They say, oh, that's just 5, since 5 times 5 is 25. We have a similar problem where taking square roots of negative numbers, if you ask most elementary and junior high kids, what's the square root now of a negative number? Of something like negative 25, now they're at a loss. They say it doesn't have a square root. They say that doesn't make any sense. So by definition, I is equal to the square root of negative 1. That's its definition. What's the square root of negative 1? It's I. What's the additive inverse of 3? It's negative 3. There's no better way I can tell you what negative 3 is than it's the additive inverse of 3. There's no better way I can tell you what I is than it's the square root of negative 1.
You can't just make shit up.
It's a definition. It's not a makeup. It's negative 1 has a notion, square root has a notion. Put these two together, call it something. I. And it follows all the rules. What's I times I? Negative 1. We define it to be that thing. The same way I define negative 3 to be the solution to this. And so there were similar rejections when I first came along.
So why didn't they just make some shit up for a number divided by 0 instead of saying it's undefined? Because it makes exactly as much sense as that.
If I allow this definition, this doesn't break existing notions. When you allow division by 0 to equal something, I can make it equal anything. So it's no longer defined. It's like, if I try to make it one word, I can make it also any word. And now it's completely meaningless. If you ever want x divided by 0 to equal some number, c, I can now make that c any number you want. Furthermore, if you make this true, then you also make x equal to c times 0, which you made 0 times c equal to some number. But that has to always be 0 if you want that to be the case. And then we showed already why 0 over 0 is still bad.
Okay, but couldn't you say that I is anything? Like,
No, I equal to this. This is a valid, this breaks nothing that we already have. For example, I already know that 2 times 0 is equal to 0.
So they just made
If
it
you
up
want
because
2
they
divided by
can.
0 equal to something, like 3, then I just barely made, or put another 2 right here. If I said 2 divided by 0, if I put some number there, 2, then I just barely made 2 equal to 0 times 2.
So I couldn't put 0 here.
So they made up I because they can't express this numerically.
It's that our current, I mean, this is a number. I is a number. The same way that negative 3 is
what
now a number.
Is it?
There isn't another way I can say it
want
other
to see
than
the
I.
number. No, I won't. Cause it.
The same way that this is a number, this is a number. And you say, nope, get rid of that. I don't want that there.
Shit. Negative 3 is a real number. It exists.
It is in the set of real numbers. This is not in the set of real numbers. It's in the set of complex numbers.
Okay, I don't care about that. I want to know what it. I mean, I know what it means. I want to know.
The same way that you can think negative 3, this right here is 1i. And the I isn't operating that much different than that symbol's operating right there. And if you want me to get rid of this symbol, that's kind of like forcing me to get rid of that symbol. It's a similar transition. Going from the naturals to the integers is kind of like going from the reals to the complex.
Can you express that numerically?
I,
Yes.
if that's how you want it.
No, that's not how I want it. I want to see. Are you being obtuse?
I don't understand what you mean by represent numerically. There is a numeral symbol, there is a numeral symbol, there is a numeral symbol, there is a symbol that you accept with your numbers. I assume you accept negative 1 as a numeral. Numeral, numeral.
Well, yeah,
I expressed
I do.
it numerically.
But that doesn't make sense. Okay, let's shift from that for a second.
Okay.
Does it have any actual usefulness?
Yes, it is absurdly useful.
How?
The complex numbers, all modern quantum mechanics is done using complex numbers. When you talk about the Schrodinger equations, they are complex functions. All of our physics on low scales, which is describing physical phenomena in this universe, is done using complex numbers. And so yes, it has tons of real world applications.
so is I equal to negative 1 to the power of 1/2?
Yeah, that's what we mean by square root, right?
That's the inverse of the square root.
No, that is the square root. The inverse of a square root is squared.
Or, yeah, excuse me.
Yeah. That's how we would define what we mean by that. We mean the positive solution of those, but because there's two.
There's no way to turn that into an actual value.
There's no way to turn it into a real number because it's not a real number. The same way that I can't turn this into a natural number.
So smart people thought about how maybe to do that.
It's a matter of definition. So the natural numbers are the numbers 1, 2, 3, etc. Those are the naturals. I can't define -3 into the naturals. Doesn't matter how smart I am, it's a fundamentally different number. I can't define I into the real numbers. It's not a matter of being smart or clever, it's a matter of, it's fundamentally something different. It's not a real number. I can't define reptiles in terms of birds. They're fundamentally different classes of things.
Dinosaurs.
Well, I guess it's not really the same because here's the complex numbers, here's the real numbers. The real numbers are a subset of the complex numbers. The same way that the naturals are a subset of the integers. Same way that here's the integers, the naturals are a subset of that.
You're saying real numbers are a subset of complex numbers?
Every real number is a complex number, not every complex number is a real number. In the
So
same
now
way,
what does complex number mean?
it has an imaginary component. Arbitrary complex number is written like this, where a and b are real numbers. So 3 plus 2i is a random complex number. But that's how they're expressed. And so any real number is just where the imaginary component is 0. So 3 plus 0i, that's an imaginary number, it's also a real number.
And not just 3.
Yeah, which is just 3, which is a real number.
So it's important to just accept this thing because it follows the rules.
It's if we call the square root of -1 something, what do we get? So let's label that thing as something, and let's play around with that value. Let's stop ignoring that. In the real numbers, we ignore that value, because it's not a real number. If we say, let's not ignore that value anymore, and see what we get if we don't ignore that value, and we call it something, I, doesn't matter what we call it, then let's look at that system of numbers now. It's very similar to what we did for going from the naturals to the integers. Let's call it something, -3. And let's see what we get with the integers. And the math we have on the integers and the math we have on the naturals aren't the same thing. You get new phenomena, things that you couldn't do before.
How do you get -3 without using a negative number?
You can't.
So then how did they come across -3?
Well, someone had the notion of, let's say that there is some number that makes this equation true.
Oh.
And we'll call it -3. Because it turns out there is no natural number that can make this equation true. See, the way the Greeks would have read something like this is, what length do I have to add to a length of 3 to get a length of 0? And they say that makes no sense.
Yeah, just
I can't have some length, add another length to that, and then get 0. And so that would have been their objection to trying to make sense out of something like this.
Well, I don't think of subtracting numbers. Makes no sense. I only think of adding negative values.
But what is a negative value?
It's an actual thing.
Show me -7 chairs.
Debt, like you said, is the best example of that.
Debt is a good example, but that's not a physical quantity in this
There's
universe.
no way they didn't understand indebtedness.
They did understand indebtedness, they just wouldn't have made the connection between, oh, let's talk about debt as a negative number. That was just intuition for you. The Greeks thought about all their mathematics geometrically. And how do you geometrically represent a negative number?
You can't.
They could do subtraction, but they couldn't do subtraction to the point where you got rid of the value altogether. So they were fine with the concept of 5 minus 3, they're fine with that. You try to do 5 minus 7, they say that's broken. Because now you get -2. And there's no such thing as a length of -2. And so the Greeks rejected the notion of negative numbers. So they still had subtraction, they just didn't have negative numbers. And they thought you could only subtract up to the number you're subtracting. Because they didn't know how to make sense out of it geometrically.
So these complex numbers are just things we're going to call them something. They do exist. They have actual values. We just can't really talk about it in that.
I don't know what to mean, what to say by they exist. They exist in the sense that any math exists, but really no math exists
When
in
I
a
say,
physical concept.
when I say exist, I mean that it's representative of some natural phenomenon.
We use it to express natural phenomena, yes, all the time.
Okay. Because I don't like stuff that it is not useful to represent or talk about some actual phenomenon.
Well, most of the time that mathematics is discovered, the associated physical phenomena that it describes isn't known. And so you had
So
Gauss,
they discover the math and then they discover the phenomenon, is that what you're trying to say?
they discovered the math, and then as a general rule, much later, someone comes across it and realizes that math is actually absurdly useful for describing this physical phenomenon. And so typically the math is way ahead of its applications, as a general rule.
So why do we need negative numbers?
You wanted to talk about that?
What if we don't want to talk about that?
Then you limit what you can talk about, fundamentally. I mean, we also use it to talk about a direction of a vector. Is a vector pointing up or a direct vector pointing down? We just throw a negative on there when we want to talk about going down.
Is there some kind of proof that you can spit out to show me that this thing doesn't break the rules?
No, you can't really prove that it doesn't break the rules. You can only prove it if it does break the rules. It's impossible to prove that an axiomatic system is consistent.
Because it seems a little inelegant.
That captures mathematics.
Okay.
I also can't prove that the definition that we have for negative numbers doesn't break the rules.
What?
I can't prove that our definition that we have for negative numbers doesn't break our rules either. It's impossible to prove that. It's proven that it's impossible to prove that.
Really?
Yep, it's called the incompleteness theorem by Gödel's incompleteness theorem. He was a logician, and he proved that any system of mathematics, any axiomatic system of mathematics complex enough to capture the basic arithmetic we want, can't be proven to be consistent. You can't prove that it doesn't ultimately lead to a contradiction.
Well, that's my whole problem with the whole damn thing, to be honest with you.
Okay?
Because it seems like math should be pretty.
Well, there's nothing that we have a better fundamental understanding of than mathematics. And yet it's proven that even with mathematics, we're limited. I mean, outside of logic directly. So I can prove propositional logic is consistent. That's something that we do in propositional logic. And you can do that with propositional logic. But by the time you get to something as abstract as mathematics, it's proven that you can't even prove it, which is pretty crazy. But it's still more sure than anything else we
Well,
have.
that's actually kind of helpful.
Okay?
Okay, thank you.
Very welcome. Okay, we'll call it there. So we'll continue from there next time. For those of you getting credit, that means exercises 1 are due next time. And I need you guys' logic.